Welcome one and all to Practice Exam 3B. So this first question, what is the molecular formula of this molecule? We're given a skeletal structure here. So remember, with skeletal structures, we assume that every carbon has its valence satisfied, so every carbon is making a total of 4 bonds. We don't have to explicitly draw the hydrogens that are bonded to those carbons. We assume that carbon bonds with enough hydrogens to satisfy its valence. So I recommend just drawing in the hydrogens just to make sure we're getting the right formula here. So let's do just that. So remember, each point of our skeletal structures represents a carbon. So as we go through, we see we've got 1, 2, 3, 4 carbons in this molecule. Now let's add in our hydrogens. We've got 3 on that carbon, 3 on that carbon. This one here only needs 1. And 2 on that carbon, which gives us a grand total of 10. Make sure that we're also including this hydrogen right here. And finally, we have 1 oxygen. So C4H10O for the win. This question asks, which of the following intermolecular forces are experienced by all molecules? So all molecules have dispersion forces. In order to have dipole-dipole interactions, we need to have a polar molecule, and hydrogen bonding, well, we'll get to that in just a little bit. This question asks about what happens when the pressure of a gas is increased at a constant temperature. And there's 2 ways to think about this. First, let's think about it conceptually. How can we increase pressure without increasing the temperature? That's right, through lowering the volume of the container. With a smaller volume, the gases are more squished together, therefore you'd have more collisions of the gases and collisions with the gases on the container wall, therefore increasing the pressure. And with them more squished together, that means you're looking at a more dense gas. Now the other way to look at it is mathematically. In this reworked form of Pivnert, recall that density is equal to the pressure of the gas times the molar mass of said gas divided by our gas constant R times the temperature. So if our temperature is being held constant, so we're just going to ignore the temperature term there, and our pressure is going up, that means that our density must be going up because the molar mass of our gas isn't going to be changing by virtue of it being that gas. So here's another way that we could answer this question. This question says, if the valence atomic orbitals of an atom are sp hybridized, how many pi bonds can it make? And there's also 2 ways we can think about this. Well, let's talk about the conceptual way, and then let's do an example. So, we can use, to figure out more, to glean more insights into hybridization, we can use our friend the SPBBD rule. So, S, P, 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 and just for kicks, D, D, SPBBD. If an atom is sp hybridized, that means it's using one of its s orbitals and one of its p orbitals. That leaves how many p orbitals available for pi bonds? That's right, not 1, but 2. Each of these unhybridized p orbitals can participate in a pi bond. So let's look at 2 examples. First, we have this carbon here that's got a triple bond. It's got 2 electron domains, so it's sp hybridized. And recall that single bonds consist of 1 sigma bond. Double bonds consist of a sigma bond and a pi bond, and triple bonds are the most delicious bonds of them all. They consist of 1 sigma and 2 pi's. So that means that our triple bond here has 2 pi bonds. So let's look at another example. Here we have another sp hybridized carbon, and it's got 2 double bonds on it. Remember, each double bond has 1 pi bond in it. So once again, it can make 2. And that is our answer. This question is about sweat and how it helps our bodies cool themselves. So sweat evaporates, and that's what cools the body. This is because evaporation is endothermic. So let's go through all the different phase changes and talk about if they're endothermic or exothermic, and then let's just talk quickly about why this is, like why the sweat works the way it does. So our three endothermic processes, the ones that we have to put heat into to accomplish, are to go from a solid to a liquid, that is melting. Like if you put heat into an ice cube, it will melt into liquid water. Going from a liquid to a gas, well, that's evaporation station. That's what we're looking at here, also known as boiling and vaporization, also endothermic. And then finally, we go from a solid directly to a gas, like what CO2 does under 1 atmosphere of pressure. That is sublimation. So all three of these processes are endothermic and have a positive delta H. Now on the flip side, let's talk about the exothermic processes. Going from a gas to a liquid, that's condensation. Going from a solid to a liquid, going from a liquid to a solid, that's freeze! Everybody clap your hands! And that's freezing. And then finally, if we go from a gas directly to a solid, that's a process called deposition. So all three of these processes are exothermic and all carry a negative delta H. So why is it that sweating works? What does it do? In order to facilitate this process of evaporation of liquid water, water on our skin takes heat from our body. So it absorbs the heat and then voila, it can evaporate off. And whoosh, look at that water go. So this question, how many sigma and pi bonds are in the molecule shown? I would recommend going through and tallying out all of these. So this is not a skeletal structure, so we don't have any hidden hydrogens. We'll have one later where we will. But in the meanwhile, let's review what each type of bond has. A single bond consists of one sigma bond. A double bond consists of a sigma bond and a pi bond. And as we said before, triple bonds are the most delicious bonds of them all. They have one sigma, and get this, not one, but two pi bonds. Let's clean that up a little bit. Okay, so let's go through and first count the number of pi bonds in our molecule here. So our pi tally, which sounds delicious, is 1, 2, 3, and 4. For our sigma bonds, remember every bond has a sigma bond in it. So I'm just going to go through and tally them out. So there's 1, 2, 3, 4, 5, 6, 7, and 8. So we have a net total of 8 sigma and 4 pi bonds. This question asks which of these diagrams depicts melting that's done via an increase in pressure. So recall that melting is when something goes from a solid to a liquid. So let's find which one it is. So looking at our phase diagrams where we plot pressure on the y-axis and temperature on the x-axis, recall that the leftmost entity is a solid. Here we have liquid, and a way that you can think of that is liquid goes into the cup. Kind of looks like a chalice of sorts there. And then finally, last but not least, we have the gaseous phase. So this choice here shows that we're going from a solid to a liquid that is melting, and it's accomplished by increasing the pressure. So this is something that could happen with, for example, ice, solid water, because water has this interesting inflection on its phase diagram where it tilts up and to the left. So if you increase the pressure to high enough, you can turn solid ice into liquid water because liquid water is actually more dense. This question asks which of these is the largest, most positive value. So if we're turning something from a solid into a liquid, we have to put heat in. The amount of heat it takes to do that is called the enthalpy of fusion for that substance. To turn a liquid into a gas, well, that's called the enthalpy of vaporization. If, on the other hand, we go directly from a solid to a gas, so we're skipping that middle phase there, that liquid here, the magnitude of this is going to be equal to the delta H of fusion and the delta H of vaporization together to get us our enthalpy of sublimation. So enthalpy of sublimation will always be equal to the enthalpy of fusion plus the enthalpy of vaporization for a given substance. This question challenges us to find constitutional isomers. So constitutional isomers, recall, are compounds that have unique connectivity of the atoms but have the same formula. So, which of these are constitutional isomers? There's two approaches that we can take this. You can always count out all the carbons and hydrogens. That's a safe way to go about doing it. And if you've got the time, absolutely a good way to do this. Another way that we can approach this is by counting the carbons and using degrees of unsaturation. So what I mean by that is, alkanes generally have the formula CnH2n plus 2. So however many carbons there are, you double that and add 2 to get the number of hydrogens. Now, we can incorporate degrees of unsaturation into this to make looking at these structures more fluid. So each degree of unsaturation can be represented by either a ring or a double bond. So however many rings and double bonds you have in a structure, that's how many degrees of unsaturation that structure has. A triple bond, there are no triple bonds in this problem, but a triple bond is worth 2 degrees of unsaturation. So let's go through and find the formulas of each of these structures. And I should quickly note that each degree of unsaturation subtracts 2 hydrogens. That's why it's called a degree of unsaturation, because it's every double bond, every ring gets rid of 2 hydrogens each. So let's go through and do this first one. This first one has 1, 2, 3, 4, 5, 6 carbons. It also has 1 degree of unsaturation by virtue of being a ring, which means instead of having the formula C6H14, like regular hexane would, this will have the formula C6H12. Okay, that's one done. Let's move on to the next one. This one has 1, 2, 3, 4, 5, 6 carbons as well. However, unlike the previous molecule, this one has no degrees of unsaturation, so this will have the traditional alkane formula, C6H14, for something that has 6 carbons. Alright, on to the next one. This one has 1, 2, 3, 4, 5, 6, 7. Ooh, a curveball! And there are no degrees of unsaturation, so the number of hydrogens will be equal to twice 7 plus 2. So 14 plus 2 is 16. That's the formula for this one. The next one, 1, 2, 3, 4, 5, 6 carbons. And 1 degree of unsaturation, meaning that it would be C6H12. And then finally the last one has 1, 2, 3, 4, 5, 6 carbons, and again 1 degree of unsaturation, so it's going to be C6H12 as well. So, our winners in this contest, the ones that are constitutional isomers, are molecules 1, 4, and 5. Each with the formula C6H12. Those are our winners here. And again, you can always go back and actually count out the number of hydrogens and find the formula. This is just kind of a quicker way that we can go about doing it as well. In this question, we have a gas law problem where we're altering the temperature and seeing what implications that has on the pressure of standard automobile tires. So anytime we're changing either the pressure, the temperature, or the volume, and we want to see what effects that has on the pressure, temperature, and volume of that gas, what we can do is use the following relationship. P1 V1 over T1 equals P2 V2 over T2. Then whatever is being held constant, we can just remove from the equation. So in this particular case, it says that we're keeping the volume of the tires constant. So I'm just going to X out the volume because we don't need it. And we get this relationship, P1 over T1 equals P2 over T2. So let's solve. Only thing to keep in mind is our temperatures are given in degrees Celsius. Is that going to fly? We need to plug in Kelvin. So we need to add 273 to both of these values. So we have 715 torr for our P1, and we're going to put that over T1, which is 23.2 degrees Celsius. And then we're going to add to that 273 because we need to make sure this is in Kelvin, which will give us the 295.2 Kelvin that we'll be plugging in to our equation. Oops, excuse me, sorry, 296.2 Kelvin. And we'll set that equal to P2, which is what we're solving for here, over temperature 2 in Kelvin, which is 291 K. So multiply both sides by 291, and we'll end up getting P2, which is 1720 torr. This question asks which of the following types of intermolecular forces are present in a liquid sample of acetaldehyde. So, up first, London dispersion forces, does it have it? Ding! By virtue of being a molecule, it has London dispersion forces. Dipole-dipole, does it have it? Ding! It does indeed, because we have this polarized bond over here with the partial negative on the more electronegative oxygen and the partial positive on the carbon. So this molecule does indeed have a dipole moment, and it is indeed polar. So, which that is kind of redundant. Finally, hydrogen bonding. To have hydrogen bonding, remember we need one of three things. Either a hydrogen bonded to a fluorine, or a hydrogen bonded to an oxygen, or a hydrogen bonded to a nitrogen. So it needs to be a hydrogen bonded to a fluorine, an oxygen, or a nitrogen. I like to think of it as hydrogen bonding is fun. Anywho, does this molecule have that? It does not. It has a carbon bonded to a hydrogen, and that carbon is bonded to an oxygen, but the hydrogen needs to be directly bonded to the fluorine, oxygen, or nitrogen for hydrogen bonding. So we only have two. We do not have the trifecta here. So this question here is about relationships and ideal gas behavior. And we're plotting one of, well, in volume in all three of these cases on the y-axis, and the number of moles, the temperature, and pressure on the three respective x-axes. So what we're going to do is use this relationship here. P1V1 over N1T1 equals P2V2 over N2T2. And recall that anything that's being held constant, we can just x out when we're considering our answer. So, for the first one, the relationship between volume and number of moles. So we're holding pressure and temperature constant in these cases. So what we get is this relationship, V1 over N1 equals V2 over N2. So this shows that there's a directly proportional relationship between these. If we were to, say, double the number of moles, the volume would have to double as well in order to keep this ratio constant. If we were to triple the number of moles, it would triple the volume, etc. So this first one, is it right? Tis not. If we wanted to make this relationship correct, it would look like this. So it is a directly proportional relationship. It would give us this linear relationship that as we increase n, the volume increases as well. But that is not what we had, so plot 1 is out. Up next, we have plot 2, the relationship between volume and temperature. So once again, we get this relationship where they're directly proportional. V1 over T1 equals V2 over T2. So, as for this plot, we're going to give it a nice green ding check, because it is right. So now let's check the last one. For the last one, we're seeing the relationship between volume and pressure. So we're ignoring actually the denominators of both of these. And we get P1 times V1 equals P2 times V2. Now, in this case, what we get is this relationship where, in order to keep this constant, if one goes down, the other one goes up. Another way of thinking about it is, if you were to compress all of the gas in a room into a small container, it's going to be very high pressure. So lower volume, with everything else held constant, lower volume means a greater pressure. So this is not the relationship we're looking for here. This one is incorrect. If we wanted to plot the correct one, it would look like this. We would have a curve that as the pressure increases, the volume decreases, and it would look like that. Again, note this is not a line, this is a curve. And such is the relationship for inversely proportional quantities. Now we're playing a game of find the functional group. It's like Where's Waldo, only not quite as much fun. So now let's go through and be functional group sleuths. Let's see what we've got. Up first, on this end, we've got this fellow right here, COOH. This is a very important functional group. It is a carboxylic acid. Cool. Next to our carboxylic acid, we have this one. This fellow here is none other than ether. But wait, there's more. What is this nitrogen doing over here? Well, this happens to be an amine, which leaves us with just one more functional group. That's this. We've got a carbonyl up here, and our carbon has a carbon to its left. It has its carbons to its right, so it's just a carbon and double bonded oxygen in the middle of a carbon chain. This is a ketone. One of the things I like about ketones is if you color them in, it kind of looks like a keyhole. It's a ketone. So the functional group not represented on here is an alcohol. In this next problem, we're trying to relate volume, temperature, pressure, and the moles of gas. We're trying to relate P and V and N and T. Wait a minute. When in doubt, Piv nerd it out! So we're going to be using the ideal gas law, the relationship that pressure times volume is equal to the number of moles times the gas constant R times temperature, making sure that we plug in everything with the correct units. So let's get to it. For our pressure, we have 1.011 atmospheres. For our volume, we have 4 times 10 to the 4th liters equals N, that's what we're trying to find here. Our gas constant R, since our pressure is in atmospheres, we're going to use 0.08206 liters atmospheres per mole Kelvin. And then finally, our temperature is 315 K. So just remember that we have to plug in Kelvin in Pivnert, not degrees Celsius. So divide both sides by the 0.08206 liters atmospheres per mole Kelvin and divide both sides by the 315 Kelvin, and we'll end up getting that N is equal to 1,564 moles, which we've got 2 significant figures here, so we're going to round that to 1.6 times 10 to the 3rd mole. This question is about a student who has these 5 different liquids and some heat is added to them, and we want to see which one has the greatest specific heat capacity. Okay, so here's how we can go about doing this. This involves the relationship Q equals mc delta T, where Q is the heat added in, M is the mass, C is our specific heat, and then finally delta T is the change in temperature. What this relationship also shows us is that if the amount of heat added is constant amongst different things, and the masses are the same amongst these different substances, the greater the specific heat is going to be, the smaller the change in temperature is going to be. So, whichever one changed the least, whichever one became the least hot, is going to be the one with the greatest specific heat capacity, which in this case is the milk. So, another way you can think about this is substances that have large heat capacities take a lot more heat. It takes more energy in order to heat them by a degree Celsius for every gram. A good example of this is water. Water has a specific heat of about 4.18 joules per mole Kelvin, or joules per gram Kelvin. So that means that it takes 4.18 joules for every gram that we want to increase by a degree Celsius. If you look at metals, metals have something more akin to about somewhere between 0.5 joules per gram Kelvin to 1 or so. Anyway, water actually has a very high specific heat. Higher specific heat means it takes more energy to heat it up by a given amount. Alright, in this question we're playing skeletal structure sleuth here. We're trying to find the number of sigma bonds and the number of lone pairs. So in a skeletal structure, if we're trying to find the number of sigma bonds, I highly recommend adding in all the hydrogens just to make sure that you're accounting for them all. So I'm going to first add in the lone pairs because anything that's not carbon or hydrogen we have to explicitly draw out. And we assume, unless otherwise noted, that all atoms obey the octet rule. So nitrogen here has 3 bonds. It would need 1 lone pair in order to have an octet. This oxygen over here would need 2 lone pairs. And this oxygen over here would also need 2 lone pairs. So the number of lone pairs present in this molecule are 5. Now, let's go through to add in all the sneaky hydrogens, and then we'll count off all the sigma bonds. So here we've added in all of our sneaky hydrogens. And now remember, every bond, every single bond, double bond, and triple bond, all of them have 1 sigma bond each. So I'm just going to go through and count off. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. I highly recommend tallying just to make sure you're counting them all. So our answer is C, 23 sigma bonds and 5 lone pairs. This question asks which of these can have a geometric isomer. So for geometric isomers, we're thinking about cis versus trans. And really quickly to go over the difference between the two. In order to tell between cis versus trans, which we don't have to do in this problem, but theoretically, if we were, what you can do is imagine a dotted line that runs parallel to the double bond and goes right through it. So I'm going to draw that in on both of these two cases. If our molecule in question has the same thing on the same side of the molecule. So here we have substituent A, and we have A again on this side. Then we end up with cis. So I like to think of same side, cis. If, on the other hand, that same substituent is found on the other side of the double bond, then we have trans. It should be noted, though, that in order to have a geometric isomer, each carbon has to have 2 unique things bonded to it. So I just wrote them as A and B versus A and C on the other side. But if you have the same exact substituent bonded to the same carbon, then you can't flip them around and have a geometric isomer because you get the same thing. So you need to have, each carbon needs to have 2 unique substituents coming off of it. Okay, so let's go through and decide which of these it can be. For the first one, here, this one has a methyl group and a methyl group coming off of the same carbon on the double bond. If we were to flip these around, we wouldn't be getting a different molecule, so not going to be that one. Over here, similar story, except here we have hydrogens. This molecule here has a hydrogen up here and a hydrogen down here. If we were to flip them, it would make no difference. Not going to be this one. All right, this one here is methyl city, methyl, 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 methyl. Guess what? Not going to be that one. This one here, we have a hydrogen here and a hydrogen here. Notice that each carbon, though, this carbon has a methyl group bonded to it and a hydrogen on it. This carbon has a hydrogen and what's called an ethyl group on it. So each carbon has 2 unique substituents, and that is the requirement for having a geometric isomer. So this one, ding, does indeed. And if we're going to classify this, we would classify this particular setup as trans. And then the last one, this is a triple bond. Triple bonds do not give us geometric isomers. You need to have a double bond, or technically a ring structure, but that's a story for organic chemistry. Ooh, this one's a good one. So this one involves a few different concepts. First of all, we need to do a mass analysis to come up with the empirical formula. Then we're going to need to use some gas law action to figure out the actual molecular formula. So first, let's figure out the empirical formula using, this relationship up here. It's 85.6% carbon and 14.4% hydrogen by mass. When using mass percentages to find an empirical formula, it's easiest just to assume that you have 100 grams total of the substance, because the empirical formula wouldn't change. It just gives us nicer numbers to work with. So if we have 100 grams total of this, we would have 85.6 grams of carbon and 14.4 grams of hydrogen. Cool. Okay, now we need to convert these into the universal currency of chemistry, the mole. There are 12 grams of carbon for every 1 mole of carbon. And hydrogen's nice cool 1 gram for every 1 mole of hydrogen. And when we do, we'll end up getting the relative molar ratio of these two things, which ends up being 7.13 mole of carbon for every 14.4 moles of hydrogen. So now what we're going to do is divide by the smallest of these values, which is the 7.13, and that will end up giving us our ratio of 2 to 1. So there's 2 carbons to every, I flipped that around, sorry. It gives us our ratio of 2 moles of hydrogen for every 1 mole of carbon. Okay, so that means that our empirical formula is going to be CH2. But this isn't asking for the empirical formula, nay, it's asking for the molecular formula. So now we need to find the molar mass of this molecule. How can we do that? Well, we're given a volume and a mass here. We're told a pressure here. We're told a temperature here. Wait a minute. We can do this one of 2 ways. Well, it both involves the same thing, the ideal gas law. We can either use pivnert to find the number of moles that we're looking at and then divide the grams by moles, or we can use the density because we're given the volume and we're given the mass, so we could convert that to density. Either way would work fine. So if you wanted to use this density of 1.15 grams per liter, you could plug this into density equals PM over RT. I'm just going to use pivnert to solve the number of moles here, but both are rooted in the same idea. And I'd be remiss if I didn't say, when in doubt, pivnert it out. So here we have pivnert with our values plugged in, 1 atmosphere, 1 liter, 0.08206 liters atmospheres per mole Kelvin, and our temperature in Kelvin is the 25 degrees Celsius plus 273, which gives us 298. So let's solve for the number of moles here. This ends up being a total of 0.041 moles of this gas. So now if we know the number of moles, check, and we know the number of grams, check, we can solve for the molar mass. So let's take that mass and we'll divide it by the number of moles. And we'll end up getting the grams per mole, which is 28 grams per mole. Cool, so now we know the empirical formula up here, and we know the molar mass, which means we can find the molecular formula. So if we look at this here, this has a mass of 14 grams per mole. That does not match our 28 grams per mole. So we need to think about how many times 14 fits into 28. Well, it fits in twice. So you can divide this by the 14 grams per mole. These numbers work out really nicely here. So we see that we have to double everything. So that means that our molecular formula ends up being C2H4. And there we have our answer. This question challenges us to figure out which of these substances will have hydrogen bonding. So remember that hydrogen bonding means we need hydrogen bonded to either fluorine or oxygen or nitrogen. Again, I like to think of it as hydrogen bonding is fun. So, which of these has this one, this motif? Choice D, a hydrogen bonded directly to a fluorine. This question gives us a big table of absorption data and asks us to figure out which ones are not greenhouse gases. So remember, what makes something a greenhouse gas is the ability to interact with and absorb infrared light. So anything that absorbs infrared is a greenhouse gas, which means NO2, O3, H2O, and CH4 are greenhouse gases. The only one, which one of these is not like the other, that does not, is N2. So N2 is the only one here that is not a greenhouse gas. Here we're looking at a Maxwell-Boltzmann distribution. And remember, the way that a Maxwell-Boltzmann distribution works is we plot percentage of molecules on the y-axis and molecular speed on the x-axis. So heavier molecules tend to move more slowly. So here, the heaviest gas is the one that corresponds to this first curve here. And notice that there's still a wide distribution of speeds here. Well, not that wide, I guess. But there still is a distribution of speeds. They're not all going really slowly. Some are going faster than others. But in general, this is skewed more toward the lower end of our Boltzmann distribution. So I like to say, the greater the mass, the slower the gas. Assuming that we're looking at the same temperatures, which these are all at 300 K. So that means that the one that has the most splayed out distribution, so this one right here, this one will notice that there's a lot more molecules that have these really fast speeds over here than the curve 1 counterpart. So this is going to be our lightest gas, with curve 2 representing something in between. So now we have to ask these questions. Which of these statements are true? Molecules in 2 have a higher molar mass than molecules in 1. Well, wait, whoa, hold the phone here. No, 1 is the heaviest gas. So, no, I'm going to put an X over this one. This one's not true. Statement B. Molecules, actually, you know what I'm going to do is I'm going to do this, because maybe more than one of these are true. Molecules in 3 have a higher average kinetic energy than molecules in 2. Okay, now, hold the phone yet again. There's a lot of phone holding here. Average kinetic energy is only dependent on the temperature that we're looking at. So, lighter gases make up for their kinetic energy by moving faster. Heavier gases, they're moving more slowly, but they have more mass, to the 1/2 mv squared. So, you know what? I don't like this statement either. These all have the same average kinetic energy. Which leaves us with C. Molecules in 3 have a higher RMS speed than molecules in 1. And I like that. That is indeed true. And remember, the way that we can find the RMS speed is you look for the highest point, so right here for this particular one, and then you move slightly to the right. So right here. And move down, that will give us our RMS speed. And we could do that for all these other gases as well. So the middle gas has an RMS speed of around 500, and the heaviest gas has an RMS speed of maybe somewhere in the neighborhood of like 400, 350 or so. Whatever, doesn't matter. This question is about what impacts vapor pressure. So vapor pressure, again, is the pressure that's exerted from when you have a liquid and there's molecules of gas that are escaping from that liquid. It's the pressure measured once we reach an equilibrium. So which of these determine the vapor pressure? The first one says the temperature of the substance. So if we add more heat to the substance, so I'm going to draw a really incredibly realistic fire effect, whoosh, whoosh, etc. Well, we're going to be adding more kinetic energy to our liquid, which means more molecules will start escaping into the gaseous phase. More molecules escaping into the gaseous phase means we're looking at a higher vapor pressure. So this first one is true. Shoot, I wasn't recording. My apologies. This particular software is a little bit unforgiving when it comes to erasing and re-recording. So rather than scrapping everything else recorded, I can't remember which part I was recording for, so I'm just going to go through each of these just to make sure that we have the full answer. So, statement 1, the temperature of the substance. That absolutely impacts the vapor pressure because the more heat you put into a liquid, the more kinetic energy it has, the more molecules are going to be able to escape into the gaseous phase. Intermolecular forces of the substance absolutely impacts the vapor pressure, because the more intermolecular forces there are, the more tightly the molecules are holding on to each other, the fewer molecules will be able to escape into the gaseous phase. So more IMFs means less vapor pressure. Which brings us to the last one, the external pressure around the substance. So whatever pressure, like for example atmospheric pressure, is pushing down, that's not going to have an impact on the vapor pressure. What that will have an impact on is the boiling point. So this will influence the boiling point, because boiling point is basically a battle of the atmosphere versus the vapor pressure. And once the vapor pressure equals the ambient pressure, then you'll have boiling. But it does not affect the vapor pressure. So the external pressure does not have anything to do with this, which means 1 and 2 only. In this problem, we have a special container that holds in one side hydrogen gas and in another side nitrogen gas, but then we mix things up and we open the divider, and we want to know the final pressure. So we're given some initial pressures here, and we're given our volumes, and we need to consider what the total pressure is going to be after we open this divider. So in order to answer this, we need to figure out the pressure from both the H2 and the N2 once the divider gets open. So let's do each of those. We're going to use this relationship P1V1 equals P2V2. So for hydrogen, initially it's 1.5 atmospheres and 5 liters. And then once we open this up, it's going to be able to enjoy the entire volume of the container, which is 15 liters. So let's solve for P2. So the partial pressure of hydrogen after we open up the container will be 0.5 atmospheres. Now we need to do the same exact thing for nitrogen. So for the nitrogen, it's 2.5 atmospheres. And starting off with 10 liters. And then we're solving for P2. Our final volume is going to be the 15 liters that we get from both the 5 liters and the 10 liters added together. And so we end up getting that the pressure of nitrogen is going to be 1.67 atmospheres. So we're almost done with this problem. There's just one more thing that we have to do. We have to find the total pressure. So just remember that total pressure of a mixture of gases is going to be equal to the sum of the partial pressures. So in this case, if we add the partial pressure of H2 and the partial pressure of N2, we'll get the total pressure. So when we do, we end up getting 0.5 atmospheres plus 1.67 atmospheres, which gives us 2.17 atmospheres. This question is about vapor pressure. And remember, as we said before, as you increase the amount of intermolecular forces in a molecule, the molecules are holding onto each other more tightly, which makes fewer molecules escape into the gaseous phase. So as IMFs goes up, vapor pressure goes down. And that's what we're going to use to answer this question. So first let's compare molecule 1 and 2. Pretty similar in terms of mass. So they both have about the same London dispersion forces. And they both have a dipole moment. What does molecule 2 have, though, that molecule 1 doesn't? If you answered the ability to hydrogen bond, you are indeed correct. So, in terms of IMFs, 1 is going to have fewer intermolecular forces than 2. Well, what about 3? So 3 is a lot like 2, except it has a whole nother oxygen on it. It's a heavier molecule. It's got more LDFs. It also has the ability to hydrogen bond. So this is going to have the greatest intermolecular forces of these 3. So then just remember that the trend for vapor pressure is the opposite from intermolecular forces. So 3, these molecules are clinging on to each other really, really tightly in the liquid phase, which means that fewer molecules are going to escape into the gaseous phase. So 3 will be the least, then 2, then 1, which gives us choice E. In this question, we're given a table that gives us the parts per million of methane and helium in our atmosphere. And then we're asked to find what is the combined pressure of these two gases if an ambient pressure is 1 atmosphere. Okay, so the first thing we need to do is find the total pressure exerted from these two different gases. So the pressure of... Actually, first, before we do that, let's find the pressure exerted by each of these gases. So we're given the parts per million of methane and of helium. So we can turn parts per million into mole fraction. So we can use this relationship. Parts per million is equal to the mole fraction of a given gas times a million. It tells us that for every 1 million particles you have, how many of them are a given gas. So let's figure out what the mole fraction is for both helium and for methane. So first for methane, which is CH4, 1.79 are the parts per million, so that's equal to the mole fraction times 1 million, so we'll divide both sides by 1 million. And we'll end up getting the mole fraction of methane is 1.79 times 10 to the negative 6th. Okay, so we'll do basically the same thing for the gas helium, and we'll get 5.24 parts per million is equal to the mole fraction of helium times 1 million. So we'll divide again both sides by a million, and we'll end up getting that the mole fraction of helium is equal to 5.24 times 10 to the negative 6th. Okay, so now we have the mole fraction of both helium and of methane. At this point, we could take one of two routes. We can either find the partial pressure of each of these gases, or what we could do is just find the combined mole fraction and then find the pressure exerted by these two. I'm going to take the latter here. So the mole fraction of both methane and helium, so the combined mole fraction of these two gases, is going to be equal to the sum of the two numbers below. So it's equal to the sum of the mole fraction of methane and the mole fraction of helium, which ends up giving us 7.03 times 10 to the negative 6. So that's the combined mole fraction of these two. So then finally, the way that we can answer this problem is remembering that the pressure exerted by a given gas, or in this case by a collection of gases, is equal to the mole fraction of said gas, or collection of gases, times the total pressure. So what we're going to do is multiply our mole fraction here by our total pressure of 1 atmosphere. So we have our combined mole fraction, 7.03 times 10 to the negative 6th, and our total pressure is 1 atmosphere, so this is a nice calculation. So we end up getting that the answer ends up being 7.03 times 10 to the negative 6th atmospheres. We also could have started this problem by adding up the ppm together. Maybe that would have been easier, and then finding the mole fraction and then converting. There's a lot of different ways to get to the right answer here. As long as we get to it, that's what counts. In this problem, we're tasked with ranking these molecules in order from lowest to highest normal boiling point. So remember the correlation between boiling point and intermolecular forces. So the more IMFs something has, the greater its boiling point is generally going to be, because the molecules are able to hold together more tightly in the liquid phase. It takes more heat to break them apart, therefore a higher boiling point. So when we're ranking these molecules, let's look at what we're given here. In terms of these first two, so the first two only have LDS going for them. They're only hydrocarbons. In addition, they're also a lot lighter than these molecules because chlorine is a lot heavier than carbon. Chlorine has 35 grams per mole, whereas carbon only has 12 grams per mole. So these ones are going to have the fewest London dispersion forces. And since they only have LDFs going for them, they are going to have the two lowest boiling points. When ranking these two, how can we put them in order? Okay, so they're both isomers of pentane, C5H12. But the one is N-pentane. It's a much more splayed out molecule. What this means is you can think of it in terms of stacking better. There's more surface area contact that these molecules can have, whereas this one right here has fewer opportunities to interact with other molecules. So it's not as polarizable. Okay, so in terms of these two, even though they have the same formula, the one that's actually going to have more London dispersion forces and therefore a higher boiling point is 2. Okay, I like to think of it as the difference between spaghetti and meatballs. This molecule here is more like a meatball. Meatballs don't get tangled up in each other, whereas this molecule here, more like spaghetti. It's longer, and that's a simplification, but anyway. These molecules have more surface area contact. Now between these two, these are geometric isomers of each other. So which one is going to have greater intermolecular forces? Well, if we look at number 4. So number 4 has a polarized bond between that carbon and that chlorine, and a polarized bond between that carbon and that chlorine. But notice how they're completely antagonistic to each other, and they completely cancel out. So there's no net dipole on this particular molecule. No net dipole. Oh no! I wonder if that's the same story for the other one. Spoiler alert, it's not. So this one has a polarized bond like that, and a polarized bond like that, which gives us an overall net dipole moment that goes this way. So not only does this molecule have our friend London dispersion forces, it also has dipole-dipole interactions available as well, which means that between molecule 3 and molecule 4, let's write it down here. So molecule 4 is going to have a smaller, lower boiling point than molecule 3. So when ranking them all together, the ones with chlorine all rank ahead of the ones with just carbon and hydrogen. So our overall ranking is going to be 1, then 2, then 4, then 3. In this problem, we're trying to relate a phase diagram with a heating curve. So to review, remember this is solid, this is liquid, and this is gas. So what's happening is we're starting with a hot liquid, and then we're vaporizing it, and then we're letting it heat for a pretty long period of time before we get to the final state. So what's going to be happening here is a 3-step process. A little bit of heating to get to there, then the vaporization, the evaporation, and then a lot more heating to get to the hotter gas. So let's see which of these diagrams matches that. So in choice A, we have here, first, we're heating our liquid a little bit. Cool. Then we get to this point where we're adding in energy. So if we look along here, we're adding in energy, heat is being added in, but yet the temperature of the substance isn't increasing. What's going on here? That's right, evaporation. So remember during phase changes are isothermic. They happen under consistent temperatures. We're adding in heat, and that's going to break the intermolecular forces. So then once we have evaporated our liquid, then finally we get to our last step, which once again is heating. But the difference between this one and the first heating was that the first one, we already had a hot liquid. We did not need to heat it that much before evaporation. But as we can see on our graph up here, once it's a gas, we heat it for a decently long amount of time, which is exactly what's going on here. So the right answer is choice A. Here we have a Graham's law problem. In this problem, we're comparing the relative rates of effusion of two different gases. So in order to figure out what our mystery gas is, we need to figure out what the molar mass is. And the relationship that we're going to be using is the rate of effusion of gas 1 divided by the rate of effusion of gas 2 is equal to the molar mass of, or the square root of the molar mass of gas 2 divided by the molar mass of gas 1. And it doesn't matter which gas you choose to be gas 1 versus gas 2. It is important that you are consistent, however. So I always like to declare my variables at the beginning of these problems. Say which gas is gas 1 and gas 2. I'm going to call nitrogen here gas 1. So that means that the relative rate and the mass R1 and M1 are going to correspond to nitrogen. And then our mystery gas is going to be gas 2. There we go. It is important to note here that we are given the time it takes for these gases to effuse. Our time's the same thing as rates. So if I were to say how fast I was driving, would I say hour? The answer is no. So a rate is equal to, in this case, an amount of effusion over a given time. It's important to note here that rate is, as we can see, inversely proportional to time. The greater the time, the slower the rate. So, we're not going to plug in these numbers directly in for R1 and R2. We're going to plug in the inverses. So for R1, we're going to plug in the inverse of nitrogen's effusion time. 1 divided by 12 minutes. And it should be noted, it doesn't matter what the value we plug in for the amount that goes through, because this is just a ratio that we're setting up here. So I'm just using 1 because that's the simplest amount to use. Divided by 1 divided by 15 minutes, so again we're plugging in the inverse of the time that it takes, is equal to the square root of the molar mass of our mystery gas divided by the 28 grams per mole of nitrogen. So it should be noted that when using the equation for RMS speed, the RMS speed is equal to the square root of 3RT divided by molar mass. Molar mass has to be in kilograms per mole. In this case, we're looking at a ratio here. So the ratio of the mass 2 over mass 1. So using grams is perfectly fine here. Just like using 1 as the relative amount is perfectly fine. We're just setting up a ratio. So I'm going to start by simplifying this side over here. I'm going to divide 1/12 by 1/15, and we end up getting 1.25. So now what we're going to do is square both sides in order to get rid of that square root. And we get 1.56 is equal to molar mass 2 over the 28 grams per mole. And then finally we're going to multiply the 28 grams per mole through, and we'll end up getting that the molar mass is 44 grams per mole. So then we see which of these mystery gases it corresponds to, and it turns out that the product of fermentation of glucose here is carbon dioxide. So if you're a biology person, you might have been able to get that problem without doing the math, but we did the math. So, moving onward. This next problem is a toughie. On this problem, we're going on a veritable adventure. We're taking 180 grams of solid ice at negative 20 degrees Celsius, and we're adding in some heat. Specifically 128 kilojoules, and we're seeing where we end up at. So this is a good opportunity to remember what heating curves tell us. So let's draw out a heating curve here. We're going to plot temperature on the y-axis and heat added on the x-axis. So where this is starting, we have a block of solid water at negative 20 degrees Celsius. As we add in heat, it will warm up until it gets to the melting point, which for water is 0 degrees Celsius. Once it reaches that point, we add in heat, but yet the temperature doesn't increase. That's because at this point, the heat being added in is being used to overcome intermolecular forces. This is the process of melting. Eventually, once we get to a liquid, we can start heating up that liquid, and again, that liquid reaches a point where we can add in heat and the temperature doesn't change. At that point, it's boiling, and it boils at 100 degrees Celsius. So we're going to take this step by step, starting with step 1, we're going to see if we have enough energy to get our block of ice to the melting point. So let's see if we do. So recall, when heating, we can use the equation Q equals mc delta T. So let's see how much energy it'll take to heat this from negative 20 degrees Celsius up to 0 degrees Celsius. So the amount of energy it'll take, Q, is equal to our mass, which is 180 grams of water, times our specific heat for solid water, which is 2.11 joules per gram degrees Celsius. And then the delta T is 0 degrees Celsius minus negative 20, our final minus our initial temperature, which is 20 degrees Celsius. So when it's all said and done, this ends up equaling 7,596 joules. Our units cancel out nicely, and we have our first step. So the question is, do we have enough energy in our energy bank to put in 7,596 joules? So we're going to divide this value by 1,000 and get 7.6 kilojoules. So now let's create an energy bank down this bottom right-hand corner. We're starting off with 128 kilojoules at our disposal. So do we have enough energy to get up to this 7.6 kilojoule threshold? You bet we do. So we are using up 7.56 kilojoules, which leaves us with 121.4 kilojoules. So we have enough, ding, to do step 1. All right, our journey continues. So after step 1, at this point we do step 2, which is melting our ice. So for phase changes, our equation is a little bit simpler. But note that if we look at our heat of fusion, right here, the units are given in kilojoules per mole. So that means that we need to make sure that we're plugging in moles, not grams. So always pay attention to units. So thankfully these numbers work pretty well. Water is 18 grams per mole. So that leaves us with 10 moles of water. Now with phase changes are actually simpler to calculate than heating a solid or a liquid or gas. The reason being is that there is no delta T because it's isothermic. The temperature remains constant. So for these processes, the heat added in is just equal to, in this case, N, the number of moles, times the enthalpy of whatever process, be it fusion or vaporization. So now let's go through and see how much energy it takes to melt our block of ice. Our Q is equal to our 10 moles of water times the 6.01 kilojoules per mole. Moles cancels out, and we're left with 60.1 kilojoules. So do we have enough energy in our energy bank to cover this cost? Absolutely we do. So we're going to subtract from this to see our new working total, the 60.1 kilojoules, and we'll get 61.3 kilojoules. Our journey continues on to step 3, which is heating our liquid. So we'll heat the liquid and keep heating it until we get to the boiling point, which I should have mentioned before. The boiling point of water is 100 degrees Celsius. So we have our 180 grams. The specific heat is 4.19 joules per gram degree Celsius. And again, the boiling point of water is 100 degrees Celsius. Let's just draw a nice dotted line to make this look a little bit fancier. There we go. And this would end up, we make sure that our units cancel out, so grams cancels out, degrees Celsius cancels out, and we're left with 75,420 joules. That's how much it would take. Which, if we divide this by 1,000, we end up getting 75.4 kilojoules. So is there enough energy remaining in our energy bank to overcome this cost? Do we have the 75.4 kilojoules needed? The answer is a resounding No, we do not. So, that means that our process is going to end up arresting somewhere in this phase. Now we need to figure out at what temperature it's going to end at. So we're going to use the same formula, but instead we're going to plug in the remaining amount of energy we have to see what that delta T could be. So for our Q, we're going to plug in the energy that we have remaining, which is 61.3 kilojoules, or 61,300 joules. We're going to set that equal to the 180 grams of water times the specific heat of water, 4.19 joules per gram degree Celsius, times the delta T that we're solving for. So we're going to divide both sides by the 180 grams and by the 4.19 joules per gram degrees Celsius, and we'll end up getting the delta T is 81.3 degrees Celsius. So that means that this is going to heat up from 0 degrees Celsius until it gets to some point in here at 81.3 degrees Celsius. At that point, we've run out of energy in our energy bank, so it's going to be a liquid, and that liquid is going to be at 80 degrees Celsius, around 80 degrees Celsius. Here we're presented with a topsy-turvy graph, where, well, it's like our heating curves, but now Q is on the y-axis and temperature is on the x-axis. Crazy! So we just need to keep that in mind. It's still a heating curve, but now in this case, so this first step is heating, then we have melting, then we have heating a liquid, then we have vaporization, then we have heating a gas. We just need to remember that our axes are thrown off here. So we're looking for the heat capacity, the molar heat capacity of the liquid substance. And so we think about what's going on here. Our substance is starting as a solid down here. At this point we have melting. And at this point we have heating of our liquid. So this is actually the part that we're going to be honing in on here to find the molar heat capacity. Okay? So, remember, for heat capacity, Q is equal to M, or in this case, since we're looking for molar heat capacity, N times C, it's molar heat capacity, so Cm, delta T. So if we can plug in a Q, we know that it's 1 mole, as given in the problem stem, and we can plug in a delta T, we can end up solving for the molar heat capacity. It doesn't matter what points on this graph you choose. I would just choose ones that end up being the easiest to eyeball the values for. So I'm going to use this point right here and this point right here in order to solve this problem. Okay, so first things first, how much heat did we add in this interval? So we went from 40 kilojoules up to 60 kilojoules. So that means that the heat added in, the Q, was the 60 minus 40, which was 20 kilojoules. Okay. For N, we were told in the problem stem that this is 1 mole of substance A. It's the Cm that we're solving for. So this is the variable that we want to find. And what is our delta T? So we can see here that this mysterious substance went from 0 degrees Celsius up to 100 degrees Celsius from these arbitrary points I chose. And you could choose any point along the way on this curve and you would still get the right answer. So our delta T is equal to our final temperature minus our initial temperature, which is 100 degrees Celsius, minus 0 degrees Celsius, which is 100 degrees Celsius. So I'm just going to plug in that 100 degrees Celsius into here. And then to solve this problem, we're going to divide both sides by 100 degrees Celsius and 1 mole. Our units will cancel out splendidly on this side, and we'll end up getting that our molar heat capacity is equal to 0.2 kilojoules per mole degree Celsius. Now at this point we need to do a little bit of tailoring of our units here. So kilojoules, our answer that, this doesn't match any of the answers that we have right now. So let's turn this into joules. So we'll multiply by 1,000 because there are 1,000 joules per kilojoule. And we'll end up getting that molar heat capacity is equal to 200 joules per mole. And then remember that a degree Celsius, a change in a degree Celsius is the same as a change in Kelvin. They're equivalent in terms of changes. So even though the answers are in per mole Kelvin, it's the same thing. So we end up getting choice D. This question asks, which of these has delocalized pi bonds? So delocalized pi bonds, what are we looking for? Resonance. We're looking for resonance. So let's draw each of these structures and see if they have resonance structures. So this first one has 17 valence electrons, so let's draw out a structure for it. We're going to put our least electronegative atom in the middle, nitrogen. We'll put an oxygen, 2 oxygens bonded to it. And then we've got 17 valence electrons, which means, let's see, 1, 2, 3, 4, 5, 6. We'll start on the outside, work our way in. So 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Each bond has 2 electrons, which means we have 1 electron left. And this is our structure. And is this a good structure? Appropriately enough, no, it's not. Look at that nitrogen. It only has 5 valence electrons. Bad. Now this is going to violate the octet rule regardless because it has an odd number of electrons, but how can we make this structure better? Well, we can make a double bond. Should we make it from this oxygen or this oxygen? Trick question. Either one works, which means we have a resonance situation. So we could either make this molecule like this, or we could make our molecule like this. Both are viable structures, which means this has resonance. So resonance means we have an electron superhighway, which means that this one indeed is going to have delocalized pi bonds. So, done with that one, on to the next one. Carbonate has 24 valence electrons. When we draw it out, we put our carbon in the middle. We'll put an oxygen here, an oxygen here, an oxygen here. We've got 6 electrons drawn in. So then we've got 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Is this a good structure? No, it's not. We can make it better. How can we make it better? Well, we could either plop these electrons in to make a double bond, or these electrons in to make a double bond, or these electrons in to make a double bond. It doesn't matter which one we do, right? So I could make it like this, or I could also put the double bond in one of these other 2 locations instead. Once again, we have a molecule that has resonance throughout it. So that means that this is also exhibiting delocalized pi bonding. So both of these are checks. Now let's look at PCl5. It's got 40 valence electrons. Our phosphorus goes in the middle. We'll put a chlorine here. We'll put a chlorine there. We'll put a chlorine everywhere. And we've got, from our 5 bonds, 10 electrons drawn in. So 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40. Okay, we're done with our structure. And no, there's no resonance here. This one is, this one's good as it is. So this one, not so much, which means 1 and 2 only. Which brings us to our last question. So this problem is about heat exchange. And we have a refrigerant. We have this chlorofluorocarbon, CCl2F2, and we're evaporating it to freeze water, 209 grams of water. And we're given the heat of vaporization of this chlorofluorocarbon, and we're given the heat of fusion of this water. So the whole key idea of this problem is when energy is transferred, we're not destroying it. So the energy that goes into one process has to come from somewhere. So the energy of an endothermic process is going to be equal to the magnitude of the corresponding exothermic process, just opposite in sign. So let's find out how much energy it's going to take, or how much energy must be lost to freeze 209 grams of water. It tells us that the heat of fusion, the energy that must be absorbed to melt ice, is 334 joules per gram of water. Now, since we're going the opposite process, it's going to be negative here. So the energy that must be lost from freezing water is negative 334 joules per gram. Furthermore, we know that we have 209, not joules, grams. Let's see how much energy this corresponds to. 69,806 joules lost. Okay, so now we're going to use this relationship up here and find the amount of refrigerant that we need to evaporate in order to facilitate this process. So the heat added in the endothermic process is going to be the negative of this. So the negative of the negative is a positive. It's going to be equal in magnitude, so 69,806 joules of energy that we need to transfer. So now let's use this relationship and find out how many grams we would need. So the heat that we're adding in is going to be equal to the mass times the enthalpy of vaporization, which we're given. We know that the amount of heat added in is the 69,806 joules. We're trying to find the mass that we need, and we'll plug in the heat of vaporization, which is 289 joules per gram. So we'll divide both sides by the 289 joules per gram and get 242 grams. But do we want grams? If we look at our answers, nay, we want moles. So let's turn this into moles. So we have 242 grams of this refrigerant that we need. And it turns out that this refrigerant is 121 grams for every 1 mole, which ends up giving us 2 moles of this refrigerant. And that concludes this practice exam. So thank you very much for watching. Keep up the great and hard work and dominate on the actual exam.